In part 1, we have generated 2 files containing small chemical compounds extracted from Wikipedia. One file was called cancer, the other antifungal. We will use these 2 files to explore DataWarrior. We first open the file cancer. To do that, you can go to the menu bar, then select File, and then open the cancer file. You should have around 280 compounds. 2 columns are now visible. One named compound name with the name of the molecules and the other named smiles with the smiles code of each compound. The names of the columns come from the headers. You can change these names within DataWarrior if you want. For example, on a Mac laptop with no external mouse, you click the Control key and then the touchpad, this opens a window, and you select Set Column Alias to rename the column. Once you have opened your file, the column structure of smiles is created and you see the molecules in 2 dimensions. We will then append the file antifungal. We go to the menu bar, select File, and then Append File, and select the antifungal file which should be on your desktop. A small window pop-up. Here we may want to rename the existing dataset name and call it cancer if it is not already, while the new dataset will be called antifungal. Antifungal should already be written in the text box, following the name of the file. This is it. Click the OK button and the new molecules are added. A new column will be created named Dataset Name. In this column, you will have cancer and antifungal molecules. We now have all the compounds, around 450 molecules, depending the version of the Wikipedia database used. Now, in the Smiles filter, to the right of the application window, the so-called filter area, you put a dot in the text box next to the command named Contains. A dot in a Smiles code identifies molecules that are not connected. It can be a mixture of molecules not chemically linked. It can be salts, it can be counter ions, or water molecules. We usually want to remove salts, solvents, and so on, because they interfere with the computation of descriptors. You select chemistry in the menu bar, and then select Extract Unconnected Fragment, a new window pop-up. You keep the default parameters, and you click OK. In doing that, a new column will be created named Largest Fragment of Structure of Smiles. We remove the dot from the Smiles text box, then we go to Data in the menu bar, and then select Delete Column. Here we want to delete the column structure of Smiles and the column Smiles. Once this is done, you select Chemistry in the menu bar, then from Chemical Structure, add Smiles code. A new window pop-up. You want to add the Smiles codes from the column structure we just created. Thus the column Largest Fragment of Structure of Smiles. Then you click OK and you have the Smiles codes without salts or water. What we did is just a small cleaning of the data, not a real data curation. To clean the Smiles code in depth, you want to use Python packages such as datamol. We won't cover data curation in these tutorials as it falls outside the scope of this introductory series on DataWarrior. If you're interested in exploring it further, I recommend checking out tutorials on this specific topic. Keep in mind that data curation can be quite challenging. When correcting errors in your Smiles strings, it's easy to unintentionally introduce new mistakes, so it's not as simple as it may seem or as it's sometimes portrayed in research articles. Now, we will save our data in a new file. We go to File and then Save. This will save a .dar file with all the data. We can call this file, for instance, merge-cancer-antifungal. We can now close DataWarrior and open it again and open the DWAR file we just created. Now we want to compute some molecular properties. Again, for a real project, you may want to perform full data curation, sanitizing and standardizing the molecules, if this hasn't already been done in the database you're using. Here, we're moving quickly to explore DataWarrior with some simple data sets. To compute properties, we select chemistry and then calculate properties. A window will open and we then select total molecular weight, log P, hydrogen bond donors, and hydrogen bond acceptors. We click OK, and this is done very fast. You can see some comments about the rule of 5 on this slide. What's important to remember is that the rule of 5 is a guideline, not a strict rule, for estimating the oral bioavailability of small molecules. It focuses on 4 key properties: molecular weight, lipophilicity or log P, hydrogen bond donors, and hydrogen bond acceptors. While it's a helpful tool in many drug discovery projects, there are many exceptions, and it's not universally applicable. For example, the rule of 5 doesn't work well for certain classes of molecules like PROTACs, which are typically much larger and violate multiple criteria. After these computations, you should have 4 additional columns with the 4 properties for each compound. Understanding how different molecular properties relate to each other is crucial in many fields, including drug discovery. One can, for instance, visualize correlations between properties. To do that in DataWarrior, you need to go to the 2D view. You can see to the right a sign plus and next to it a tool icon. When you hover your mouse over that icon button, a tooltip window pops up. This button is named Configure View. So if you click on Configure View, a window will open. Select Set Statistical View Options. You select Show Correlation Coefficient and select Pearson. By default, in the 2D view window, the plot should be set to Scatter Plot. We keep this as it is. For the Command Display Line or curve you select Fitted Line. We then click on Display Standard Deviation and we keep all the other parameters as they are and then click OK. We want to see how much variability there is around that fitted line. Then we click on the XY icon and set X to log P and Y to total molecular weight. And you click again on the icon XY to hide the window, and this is it. You can resize the 2D view if needed. You see that R, the correlation coefficient, is around 0.6. Correlation measures the strength and direction of a relationship between two variables. In DataWarrior, different types of correlation values can be computed. You can select Pearson correlation or Spearman rank correlation in DataWarrior. Here we use Pearson. The sign plus and the value 0.6 indicate a positive correlation, and when the molecular weight tends to increase, log P also tends to increase. Now we want to color the molecules by category. We have 2 large families, the cancer molecules and the antifungal compounds. We look at the 2D view window, we click on Configure View, a window opens, we select Marker Color, we will color them by dataset name, and we also select Color by numerical categories, and we click OK. We should have the antifungal in blue and the cancer compounds in red. This can be changed by clicking on the color boxes. If we want to change the value range, for example for the y-axis, we can go to Data and set Value Range. Maybe we want to put 0 for the minimum value and 800 for the maximum value. With this, we will see better all the circles, thus all molecules, in the plot. If you put the mouse over a circle, you will see the molecule in 2 dimensions on the right side of the application window, below largest fragment of structure of smiles, and just above, in the data window, you will see the values and name of that specific compound. When a molecule is selected in a figure, the corresponding row on the table is also selected. A correlation matrix can be computed to show the correlation coefficients between each pair of variables. To do that, you select Data and then Show Correlation Matrix, and you can click New File. A new window is created and you see all the correlation values. The size of the circle is proportional to the coefficient value. You can click on the Configure View icon next to the plus sign in the 2D view window, then use the command Set Marker Color and color by Pearson coefficient and click OK. And now you can close this window. Imagine, instead of log P, we have docking scores, and if, for example, they were found to highly correlate with, for instance, the molecular weight, this would suggest that the docking scores may be biased or highly influenced by size rather than strictly reflecting binding affinity or quality of molecular interactions. In this case, it would be important to investigate further these docking scores and run additional computations. Now, let's return to the rule of 5. In DataWarrior, we can choose to compute values using a custom formula. For example, we may want to find compounds that do not comply to 2 or more descriptors of the rule of 5. You can find help in the DataWarrior forum if you need to compute something like this. There you can find solutions proposed by the DataWarrior community. Thus, you can go to the menu bar and select Data, then add calculated values. In the text box, you can write the formula shown in the slide. You give a name to the new column, for example, rule of 5 info, and then you click on the OK button. You will see which molecules are accepted or rejected following these criteria. Now, we will create a new 2D view by clicking the plus sign icon on the existing 2D view. In this new window, you then click the icon Configure View next to the plus sign icon and select Preferred Chart Type and then select Pie Chart and you click the OK button. Then on the XY icon, select the column rule of 5 info and let the second value to unassigned. Then on the Configure View icon again, select Set Marker Color and color by dataset name. Now we will save this figure in a file. To do that, we go to the plus sign icon and select Copy View Image. A small window will pop up and you can, for instance, save the image as a PNG file. We can compute some other type of drug likeness. In DataWarrior, drug likeness is computed using a fragment-based approach, as you can read on the slide and in the user guide. If a molecule contains fragments that are common in real drugs, it gets several positive scores. And if a molecule contains essentially fragments that are common in simple building blocks but rare in drugs, it gets a negative score. To compute drug likeness, you select chemistry. Then from chemical structure, calculate properties and select drug likeness. If we take one example, compound, it can be rejected by the rule of 5 calculations and yet have a positive drug likeness value. Both information are valuable. The rule of 5 and drug likeness score are looking at different things. The two scores are complementary, not interchangeable. The drug likeness score evaluates structural similarity to known drugs. In a way, the rule of 5 evaluates somewhat pharmacokinetic potentials. A good drug candidate ideally scores well in both, but exceptions exist. Plus, these scores and rules are guidelines, not dogma. This compound here is not FDA approved, I believe, and was not administered orally in human during clinical trials. Next, we'll check whether our compounds contain PAINs or pan-assay interference compounds. These are molecules known to frequently produce false positives by interfering with multiple assay types, often hitting many targets in a non-specific way. As a result, they are generally considered undesirable in drug discovery and may not be suitable for clinical development. However, it's important to note that PAINs filtering remains controversial. Some argue that it may lead to premature dismissal of potentially valuable compounds, and the debate over whether to strictly exclude or carefully evaluate PAINs is still ongoing in the scientific community. In this figure, taken from a Nature paper, you can see examples of PAINs structures and substructures. To search for PAINs in DataWarrior, you select Chemistry, then from Chemical Structure, calculate Properties. You will see a new window, and you can select PAINs. You can also search for the presence of nasty chemical groups in DataWarrior. However, to explore further toxicophores, it will be valuable to use a Python package like Datamol. That's it for today. Thanks for following along, and best of luck as you dive deeper into DataWarrior. There's still a lot more to explore, so stay tuned. I'll be sharing more tutorials to continue our journey with DataWarrior and help you explore its potential.